Why is it harder to push a full shopping cart than an empty one? Why does a baseball go so much faster than a bowling ball when you throw it? These questions all have the same answer, and it's one of the most important rules in all of science. Newton's second law of motion. This isn't just a random fact. The standard HS-PS2-1 requires us to analyze data to prove that there is a solid mathematical relationship between how hard you push, force, how much stuff is in the object, mass, and how much its motion changes, acceleration. That's our whole goal today, to find and prove that relationship. So, let's start with the basics. What is a force? It's just a push or a pull. It's that simple. When you open a door, you're applying a force. When you lift your backpack, you're applying a force. Even gravity, just sitting there, is pulling you down with a force. The key thing to remember is that force is a vector. This is a fancy word meaning its direction matters just as much as its strength. Pushing a shopping cart forward is very different from pushing it to the side. 10 pounds of push to the right is not the same as 10 pounds of push to the left. We have to keep track of both. The next piece of the puzzle is acceleration. Most people think this just means speeding up, but in physics, it's much more. Acceleration is any change in velocity. Since velocity includes both speed and direction, there are three ways you can accelerate. You can step on the gas in your car, that's acceleration. You can also hit the brakes. Slowing down is also a type of acceleration. We just sometimes call it deceleration. And finally, even if your speed is constant, if you turn the steering wheel, you are accelerating because your direction is changing. All three, speeding up, slowing down, or turning, are caused by a force. What about mass? Again, it's not what most people think. Mass isn't your weight. Mass is the amount of matter or stuff in an object. The more mass something has, the more it resists being moved. This resistance is called inertia. Think about it in space. An astronaut is weightless, but they still have all their mass. If you try to push that astronaut, it's still hard. If you try to push a weightless space station, it's impossible for one person. The space station has enormous mass and therefore enormous inertia, even though it has no weight. Let's nail down this difference between mass and weight, because it's the number one most confused concept. Your mass is a fundamental property of your body. It's the kilograms of you. That number is the same whether you're on Earth, on the moon, or floating in deep space. Your weight, on the other hand, is a force. It's the force of gravity pulling on your mass. On Earth, gravity pulls hard, so you have a high weight. On the moon, gravity is much weaker, so your weight is only about 1/6 as much. Even though your mass is exactly the same. You're made of the same stuff, you're just being pulled on less. In the real world, you're almost never dealing with just one force. Think about a tug of war. You have one team pulling left and another team pulling right. The net force is the overall result of this battle. It's the sum of all the forces. If Team A pulls left with 100 newtons of force and Team B pulls right with 80 newtons, they don't cancel out. The forces are in opposite directions, so we subtract. The net force is $100, $80, $20 newtons to the left. That 20N is the unbalanced force that will actually cause the rope to move. When the net force is zero, things are balanced. Imagine that tug of war again, but this time both teams are pulling with exactly 100 newtons. The net force is $100, $100, $0. The rope doesn't move. The forces are balanced. This is also true for a book just sitting on a table. Gravity pulls it down, but the table's normal force pushes it up exactly the same amount. The forces are balanced, the net force is zero, and the book's motion doesn't change. An unbalanced force is when one side wins. This is when the net force is not zero, and when that happens, the object accelerates. This leads us right to Newton's first law, which you've probably heard before. It's the law of inertia. It basically says objects are lazy. They want to keep doing whatever they're already doing. If a soccer ball is at rest in the grass, it will stay at rest. If a satellite is moving in space, it will keep moving in a straight line at that same speed, unless, and this is the big unless an unbalanced force acts on it. A kick, an unbalanced force, makes the soccer ball move. The friction from the grass, an unbalanced force, makes it stop. The first law tells us what happens when forces are balanced, A $0. So, if the first law tells us what happens when FF for net dollars is zero, the second law tells us exactly what happens when it's not zero. This is the core of standard HS-PS2-1. It's a two-part relationship. First, acceleration is directly proportional to the net force. That means if you push harder, you accelerate more. Double the force, double the acceleration. Second, acceleration is inversely proportional to the mass. That means if the object is heavier, more massive, it accelerates less. Double the mass, get half the acceleration. This entire complex relationship is summarized in one beautiful simple equation. F power net dash m on times a dollars. Net force equals mass times acceleration. This is it. This is the mathematical model that HS-PS2-1 asks us to verify. The F net on the left is the cause. It's the unbalanced push or pull that results from the battle of all forces. The M and at on the right are the effect. That net force is applied to a certain mass, and the result is a change in motion or acceleration. Let's look at the units. Mass is in kilograms, kg. Acceleration is in meters per second squared, m². So what is force? It's a kg rc dot m². That's kind of a mouthful. So scientists named this unit the Newton, or N, after Sir Isaac himself. What does 1 Newton of force actually feel like? Well, if you have a 1 kilogram mass, like a big textbook or a 1 liter bottle of water, and you push it just hard enough to make it speed up by 1 meter per second every second, that push is 1 Newton. It's not a lot of force, roughly the weight of a small apple. Let's prove the first part of the law. How are force and acceleration related? They are directly proportional. Think about one single shopping cart. Its mass is constant. If you push it gently, you get a small acceleration. If you push it twice as hard, you get twice the acceleration. If you triple the force, you triple the acceleration. If you plotted this on a graph, with the net force you apply on the x-axis and the acceleration you measure on the y-axis, you would get a perfect, straight, diagonal line. A straight line graph is the smoking gun that proves a direct proportion. This is what the standard means by analyze data. Let's imagine we're in the lab. We take a 2 kilogram cart, we pull it with a 5 Newton force and measure the acceleration, 2.5 m's $2. Then we pull with 10 newtons and measure 5.0 m's $2. Then 15 newtons and we get 7.5 m's $2. What does this data tell us? Let's check the relationship. What's F divided by $8? In the first trial, $5, 2.5 sacra $2. In the second, 10, 5 sec $2. In the third, 15, 7.5 sec $2. The ratio is constant and it's equal to the mass of the cart. This data proves that Fa dart chirem, which is the same as F dart chir dart mad. Now for the second part of the law, how are mass and acceleration related? They are inversely proportional. This time, you're going to push with the same constant force. Let's say you're pushing as hard as you can, consistently. First, you push the empty cart, low mass. It accelerates quickly. Then, your friend fills the cart up, high mass. You push with the exact same force, but what happens? The cart barely accelerates at all. You increase the mass and the acceleration went down. That's an inverse relationship. Let's look at the data for this experiment. We're going to use a constant 10 Newton force, first on a 1 kilo mass. Our equation A Fm$ predicts 1 out 10 ms $2. And that's what we measure. Now, on a 2 kilo mass, we measure $5 min s $2. On a 5 kilo mass, we get $2 min s $2. On a 10 kilo mass, we get $1 min s $2. Let's analyze this data. The relationship is A bez Fm, or mem 1 times A out F. Let's check. Trial 1, $1 times 10 out $10. Trial 2, 2 or times 5 $10. Trial 3, $5 times 2 $10. Trial 4, $10 times 1 $10. The product of mass and acceleration is constant, and it's equal to the net force we applied. This data proves the inverse relationship. The best thing about F part $, is that it's an algebraic equation. As long as you have 2 of the 3 variables, you can always find the third. A simple way to remember how to rearrange it is the formula pyramid. Just draw a triangle. Put $5 on top. Put manos and $8 on the bottom. Now cover up the variable you're trying to find. If you want to find $5, cover it and you're left with m$ times $8. If you want to find $8, cover it and you're left with F$ over M$. If you want M$, cover it and you're left with F$ over L$. Let's try a real problem. A 1500 kilogram car has a net force of 3000 newtons pushing it forward. What's its acceleration? First, we identify our variables. The mass EMOs is 1500 kilos. The net force F ER net is $3,000 N. We're looking for A delos. Using our pyramid, we cover A elas and see the equation is A dou F M dou. So we plug in the numbers. A day $3,000 N dollars divided by $500 kilo. The math is simple. $3,1500 $2. The units are M S $2. The car accelerates at 2 meters per second squared. Let's try one more going the other way. A 0.15 kilogram baseball is hit by a bat. In the tiny fraction of a second it's on the bat, it accelerates at an enormous $20,000 mass $2. What net force did the bat apply? Again, identify. Mass is 0.15 kilos. Acceleration as is 20,000, mount is $2. We're looking for F net, none. This time our equation is F net, M un times A dollar. So F net is 0.15 un times $20,000. That gives us a net force of 3,000 newtons. That's a huge force, but it makes sense for such a violent impact. It's really important to remember the F times net to a part of the equation. In the real world, you're always fighting against friction. If you push a heavy refrigerator across the floor, you might be pushing forward with 300 newtons of force, but friction is pushing backward with, say, 250 newtons. The refrigerator doesn't accelerate based on your 300 N push. It accelerates based on the net force. The net force is $300 N dollars forward minus $250 N dollars backward, which equals only 50 N. That 50 N is the unbalanced force that F plus MA actually uses. If you only pushed with 250 N, exactly matching friction, the net force would be zero and the fridge would not accelerate. It would either not move or slide at a constant velocity. So let's bring it all home. The core standard, HS-PS2-1, asks us to prove the link between force, mass, and acceleration. We've done it. That link is the equation F to net M n times A dollar. It's not just a formula to memorize, it's a model that describes how the universe works. We can support this model by analyzing data from experiments. That data shows us clearly that if you increase the net force, you proportionally increase the acceleration. They have a straight line graph. And if you increase the mass, you inversely decrease the acceleration. They have a curved line graph. This data proves the law.